Every team building on language models runs into the same wall eventually. The demo works beautifully. The model writes something smart and readable, and then you try to feed that answer into an actual system, and everything falls apart. That's the problem this whole session is about, and it's a lot less glamorous than most AI content you'll see. Over the next few slides, we're going to build a map of how people solve it. The title says landscape for a reason. There isn't one blessed technique here. There's a spectrum, and where you land depends on how much failure your system can absorb. Underneath the title, you'll see the 4 colored chips. Those 4 bands are the organizing idea for everything that follows, running from simply asking the model for a format, to declaring a formal contract, to having the provider enforce it during generation, to validating typed objects in your own application code. We'll keep coming back to those colors so the map stays in your head. My promise for this deck is a clear big picture rather than deep detail on any one method, because 11 notebooks are waiting to give you the detail. Let's start with why any of this is necessary. It's worth being blunt about the starting point, because a lot of tutorials skip it. A language model is trained to produce text that reads well to a human, and that objective has almost nothing to do with what the rest of your stack needs. On the left, you can see what actually comes back. Prose, a friendly preamble nobody asked for, some stray markdown fencing, and a shape that quietly changes between one call and the next. It's genuinely good writing. It's also unusable as a payload. In the middle sits the part most teams underestimate, the gap. This is where people write brittle string slicing, wrap everything in a try block, and retry until something parses. That code isn't engineering, it's superstition, and it's the single biggest source of silent breakage in agent systems. On the right is what the things downstream actually require: predictable keys, predictable types, something a parser can consume every single time, and a failure mode that shouts instead of quietly handing back nonsense. Notice these 2 panels aren't slightly different. They're different in kind. Closing the gap isn't a prompt tuning exercise, it's an architectural decision, and the rest of this deck is about which architecture you choose. The bottom line is simple. Your APIs, your database, and your UI don't read English. They read schemas. Once you accept that structure has to be engineered rather than requested, the obvious question is how. The honest answer is that there are about 11 common techniques, and dumping 11 names on you at once is a great way to remember none of them. So here's the organizing frame we'll use for the whole course. 4 tiers, arranged by 1 variable, how strong the guarantee is. At the top, in blue, you simply ask. The format lives in the prompt, nothing enforces it, and the model can wander off whenever it likes. 1 step down, in teal, you move from a request to a declaration. JSON mode and JSON schema write the shape down formally, so at least everyone agrees what correct means. Down again, in orange, the enforcement moves inside the generation process itself. The provider constrains which tokens are even legal, so producing an invalid shape stops being possible, rather than merely being discouraged. And at the bottom, in navy, you stop trusting the model altogether and validate in your own code, turning whatever came back into a typed object or an explicit error. Read the stack top to bottom, and you're reading a line from weak promise to hard guarantee, and, not coincidentally, from cheap and portable to more effort and more lock-in. Keep these 4 colors. Every remaining slide uses them. Almost everyone starts here, usually without realizing it's a technique at all. You write a prompt, you say, please return your answer as JSON with these fields, and quite often it works. That success is exactly what makes this tier dangerous. It's convincing enough to ship and weak enough to break in production. Looking at the 2 cards, the first approach is straight instruction. You describe the fields you want in plain language, and the model does its best. It costs nothing, needs no SDK support, and runs against literally any model you can reach, including small local ones. The second approach is few-shot formatting, and it's meaningfully stronger. Rather than explaining the shape, you show 2 or 3 worked examples, and the model imitates the pattern. Imitation genuinely outperforms description here, because the examples pin down the edge cases your explanation forgot. On the right, you'll see where we are on the map. The top band is lit, the rest is gray. That position tells the real story. Nothing in this tier is enforced. One unusual input, one long conversation, one model version bump, and the format quietly drifts. Use these techniques to prototype in minutes. Just don't confuse a technique that usually works with one you can depend on. The moment prompt instructions start failing at scale, the natural next move is to stop asking and start declaring. That shift from request to contract is what this tier is about, and it's where most teams' production journey really begins. The first row is JSON mode. It's a provider-level flag, and it does exactly one thing. It forces the output to be syntactically valid JSON. No fences, no preamble, no trailing prose. That alone eliminates a surprising fraction of your parsing bugs. But read carefully what it doesn't do. It says nothing about which keys appear or what types they hold. You'll get valid JSON of whatever shape the model felt like. The second row is JSON schema, and this is the real step forward. You write down the keys, the types, and which fields are required. Now the shape isn't implied by a paragraph of English. It's a document both sides can point at, version, and test against. That's genuinely valuable even before anything enforces it, because it turns a vague expectation into a reviewable artifact. And that's the catch worth sitting with. A schema you can't enforce is still just a strongly worded preference. And valid JSON is not the same thing as correct JSON. If your system can tolerate the occasional wrong field, this tier is a fine place to stop. If it can't, keep going. Here's where the guarantees stop being social and start being mechanical. And honestly, it's the most interesting engineering in this whole space. Follow the 3 steps left to right. First, you hand the provider a strict schema. Same artifact as the previous tier, but now it's going somewhere that will act on it. Second, that schema gets compiled into a decoding grammar, essentially a set of rules about which tokens are legal at each position given everything generated so far. Third, and this is the crucial move, at every generation step, the illegal tokens are masked out of the distribution entirely. The model isn't being asked to behave. It structurally cannot emit a closing brace in the wrong place or a string where an integer belongs, because those tokens aren't on the menu. Native structured outputs from the major providers and open constrained or grammar-based generation are 2 flavors of this same idea, just implemented at different layers of the stack. Now the trade-off, because the hype around this tier tends to skip it. The guarantee is real, and it's the strongest one available, and the lock-in is equally real. You're depending on a specific provider's implementation, and complex schemas can push the model towards stilted content, even while the shape stays perfect. What's genuinely changed here is location. Enforcement has moved out of your prompt and into the decoder. Now a slight detour, because one of the most widely used structured output mechanisms in production isn't usually filed under structured outputs at all. When you do function or tool calling, you never actually ask for JSON. The interface itself does the structuring, and that's a meaningfully different paradigm. Walk the pipeline. You start by declaring a tool, a name, a description, and typed parameters. The model then decides whether to call it and fills in the arguments. Those arguments come back as a structured, validated argument object, rather than a blob of text you have to rescue. Finally, your code executes and the result feeds back into the conversation. Every major provider has hardened this path because agents live or die on it, which makes it, in practice, the most battle-tested structured route available to you today. But there's a real limitation, and it's worth naming. What you get is an action interface, not a document format. If your actual goal is a structured report or a classification result, expressing that as a fake tool call works, but it's a workaround wearing a costume, and it distorts how the model reasons about the task. So the decision is clean. If the output is meant to trigger something, a query, an API call, a state change, tool calling isn't just a valid option, it's already the right one. Every tier we've covered so far shares a hopeful assumption that the model is going to hold up its end. This last tier drops that assumption entirely and moves the responsibility into your own code, where you actually control what happens. The first card is Pydantic. You define a model with real Python types, add constraints and defaults, and what comes back isn't a dictionary you have to keep checking. It's an instantiated object with fields your editor can autocomplete and your tests can rely on. Coercion handles the small mismatches, and anything genuinely wrong raises immediately. The second card covers data classes and lighter typed models. Less machinery, standard library only, and a good fit when you mostly want shape clarity rather than heavy validation. Then, look at the callout. Every failure this tier catches surfaces inside your code at a line number with a stack trace, not 3 services downstream at 2 in the morning. And be clear-eyed about the limitation on the right. Validation happens after generation, so it can't prevent a bad output, only stop it from spreading. That's precisely why the strongest systems pair it with Tier 3 rather than choosing between them. Enforce during generation, then validate on arrival. Not every situation gives you the luxury of a cooperative provider. Older models, self-hosted deployments, cheaper endpoints, or a legacy integration you inherited, plenty of real systems simply won't emit clean structure no matter how you ask. Output parsers exist for exactly those cases. Reading the flow left to right, you start with raw model text, and the dashed border is deliberate. It's loose, unreliable, and full of things you didn't want, like code fences and helpful commentary. In the middle sits the parser, doing unglamorous work, stripping fences, pulling out the JSON-looking region, coercing types, mapping fields onto the names your code expects. Out the right side comes something typed and usable. Now the honest assessment underneath. Parsers are compatibility glue, not a structure strategy. They don't make the model more reliable, they just clean up after it. And their failure mode is nasty, because they break quietly the moment the model rephrases its output in a way your extraction logic didn't anticipate, often without raising anything at all. So treat them as a bridge with an expiry date. Use them to reach models you can't otherwise use, and retire them the moment a real enforcement path opens up. Let's talk about the thing most structured output content carefully avoids. None of these methods is perfect. Even the strongest enforcement can hand you a perfectly shaped object full of wrong values, and mature systems are built around that reality, rather than in denial of it. The loop shows the 4 moves. You validate first, parse the response against the schema, and find out immediately whether it holds. When it doesn't, you diagnose which field failed, what type was expected, what actually arrived. That detail matters, because step 3 is repair or retry, and the trick is feeding the specific error message back to the model, rather than blindly asking again. Told exactly what it got wrong, models correct themselves at a surprisingly high rate. And then the step people forget. Give up well. Cap your attempts, log the failure, return a clean error. An unbounded retry loop against a metered API is how a bug becomes an invoice. The orange return path is deliberately marked bounded and logged, and I'd argue this loop is the single highest leverage piece of code in the whole pipeline. No method reaches 100%. The systems that survive contact with reality are the ones that planned for the 2% that doesn't. So, with 11 techniques and 4 tiers on the table, how do you actually choose? Not by whatever shipped most recently, and not by whichever approach got the loudest launch post. Choose by constraint. The columns give you the 4 that matter in practice: how reliable the result is, what it costs you in effort, and how portable you stay. Tier 1 is minutes of work and runs against anything, and its reliability is exactly as low as that convenience suggests. Prototypes and internal tools, fine. Tier 2 asks for a few hours and buys you a real contract with reasonable portability across providers. Tier 3 gives you the strongest guarantee available and charges for it in lock-in, tying you to a specific provider's implementation. Tier 4 is fully portable because it's just your own Python, and its reliability is high but retrospective. It catches problems rather than preventing them. Read across the rows and you'll notice the last 2 aren't really competitors. Enforcement during generation and validation on arrival address different halves of the same risk, which is why most serious production agents run both, belt and braces, rather than betting everything on one clever trick. Start at the weakest tier your failure budget can genuinely absorb, and move down only when reality forces you. So that's the landscape. 4 tiers, 1 axis. You can ask for structure, declare it as a contract, enforce it during generation, or validate it in your own code. And the further down you go, the harder the guarantee, and the higher the price and effort or lock-in. The takeaway I'd want you to leave with is a decision rule rather than a favorite. Choose the weakest tier your failure budget can actually survive, and combine tiers when the stakes justify it. From here, 11 notebooks follow this deck, one per method, in roughly the order we walked through today. Each one is hands-on, so you'll write the prompt, break it, then watch a stricter tier fix what broke. You've got the map now. The notebooks are the terrain, so let's go run some code.